absorptivity instead of concentration?
Yeah.
What, so, are there any others that you can just replace instead of
No,
concentration?
no. We just did that in that special case because we didn't know what the concentrations were. Absorption is equivalent to it, or
Does that always
Does
work
that
on
work?
absorptivity?
for absorption, yes.
Alright.
Yep, it does.
Nothing else?
No, not that I can think of. Not that we'll measure. No. Okay, so what we're going to try to do, part A, down at the bottom, after they give you the experimental data, they say A, B, C, D, and then Mr. Hevel added E in there, which we're not going to do E because it's a little bit confusing. A, what is the order of the reaction with respect to HgCl2, with respect to C2O4, and overall? What that means is they want the order. And we're going to be using this concept. If we find that one of the reactant concentrations doubles, but the rate doesn't change, that means that that reactant is zero order. If doubling the reactant concentration causes the rate to double, that was first order, like that. And then, you remember talking about that and doing that? Okay. So I have a little template here for filling out. I would suggest we use trials number 1 and 2 to find oxalate's order.
And then 1 and 2?
Why would I choose 1 and 2 for oxalate?
Because you see that times 4.
What's that?
You see that times 4.
Yeah, but also, notice that the HgCl2 is held constant. You don't want both of them changing at the same time. You just want one of them to change so you can see what its concentration does to the rate. You see what I mean? So let's go ahead and look at trials 1 and 2. So trials 1 and 2, only the oxalate concentration is changing. It's doubling. What's happening to the rate? If you're not sure, take your calculator and divide. Trial 2 rate divided by trial 1's rate. It's going up by 4.
Second.
So, right, that makes it second order. If doubling the concentration caused it to go up, the rate to go up by 4, that means it was a second order reactant. Let's look at the HgCl2. We would need to find its order too. How does the concentration of HgCl2 affect the rate? Well, we could use trials 2 and 3. I chose to use trials 1 and 4. Both of them would work. I like 1 and 4 better because the rate numbers are easier to see. In trials 2 and 3, you see how the exponent on the 10 changes? Sometimes people get messed up by that. So I'm trying to stay away from that. Do 1 and 4.
Also, it's more exact.
Yes. So the oxalate is held constant in trials 1 and 4, and the HgCl2 doubles. Doubling the HgCl2 does what to the rate? It doubles it. Right. So that makes it first order. We haven't really done anything with the overall, and I'm going to have to talk about this next week. But the overall is where you just add the two orders together. So overall, that would be a third order reaction. Again, we don't know what that means yet. Really, even if you think you do, you don't. We have to talk about what that means. Actually, it has to do with the mechanism of reaction. Yeah.
So if you had like 10 reactants, and then like each one was like second order, it would be 20 order.
Yes, overall of 20. Yep. When you find what the order of a reaction is, though, you'll find that it's very unlikely. Even to have a third order reaction is really unlikely. I guarantee this is a very slow reaction. But we'll find out why later. Okay? Can't go into it yet, but we will.
Is this what you meant by...
I know you're watching the clock, John. You especially, aren't you? Is it time to leave yet?
No, no, no.
Oh, you're going to be gracious and give me one more minute. Thanks.
So when we compare the concentration, when we try to find the order of HgCl2, we make the C2O4 a constant, right?
Yeah, you want two trials where that's a constant, and only the one reactant is changing. Yep. Okay. Now, the rate. Now, Part B says write the rate expression. That means the rate law. It's going to look like this: rate equals K times the concentration of C2O4 to the second power times the concentration of HgCl2 to the first power. That's it. That's the rate. It did call it in the problem the rate expression. It's the same thing as the rate multiple. And then for part C, the question is calculate K for the reaction, including units. Now, on the previous slide, and you have this written down, to find K, you find the order first, which we did, and then just choose one trial and plug in the numbers for it. And the only thing you won't know is K. So look at how easy this is. This is so incredibly easy. You just can't get this wrong. I choose trial 1. And you'll notice trial 1 has 0.1 and 0.1 for the concentration. The numbers are just the easiest in trial 1. You could use any trial. I always just look for the easiest numbers. Very quickly, I know I'm out of time and you're going to get up and walk out of here. Please don't. I guess I told you you could before. The rate is 1.3 times 10 to the negative 7. That's molarity per second. And that's equal to, okay, now all I'm doing is taking this thing and rewriting it, but plugging numbers into it. And again, the whole reason is so we can find K. The question is, what is K? What's that rate constant? So I'm plugging in the data from trial 1. The HgCl2 is 0.1, and that's to the first power. Oh, I wanted to put molarity on there. And then times the C2O4, which is 0.1 squared. Now I know that I have turned it around here. It doesn't matter what order, you just multiplying these numbers. But truth, are you sure you have to ask?
Isn't it mole over liters 10 seconds?
Yeah. If you want to be a disciple of the Zoomdalls, then go for it.
1.3
Now-
times 10 to
Thank you. Jennifer has already been nice enough to do this calculation. Solving for K, just dividing all that out. Now what did you do with the units?
the those cancel out, right? Those Ks.
1 over
Now I got molarity per second over here, and over here I have what unit?
molarity cubed.
It's molarity cubed. Ugh. So when I divide over here by molarity cubed, I have a molarity there and a molarity cubed on the bottom. So yeah, then one of the molarities cancels out. And you wind up with a unit that looks like this. 1 over molarity squared seconds.
So every order you're dividing by.
Yep. The Zoomdalls would say liters squared over moles squared seconds. And you'll see that in the solution guide. Okay, then for part D, it says, when the concentrations of both reactants are 0.3, what is the rate? This is so easy, I won't even do it with you, because you now know K from that part. They're telling you to plug in 0.3 there and 0.3 there and solve for the rate. Come on. It's so easy. That's how we do differential rate law. You do have to kind of get the hang of it, but you know what? It's pretty easy. And man, I wish I had a little more time to show you another example, but I quit.
Wait.
Yeah.
When they say find rate, are we trying to find K? Or are we finding 1.3?
No, find the rate. So find the left side of the equation. You're going to plug in K. K doesn't change. Now that you found K, you're going to use that for this reaction. So you're going to solve for this. The question is, what is the rate? That's that.
Don't we already know the rate is 1.3 times 10 to the negative 7?
Yeah, when the concentrations are 0.1 and 0.1.
Right.
But in part D, they say, what if the concentrations are 0.3 and 0.3?
Oh, okay, I see what you're saying. My bad.
Determine the initial rate.
Yeah, I told you we're not going to do that one. It's confusing.
My bad.